first understand what is electrogravimetry. So here, uh, electrogravimetry, the name as the name implies, gravimetry is always associated with the weight of the product or the weight of the material that we are dealing with. So here, electrogravimetric analysis, it is more or less similar to that of the gravimetric analysis. But in electrogravimetric process, we conventionally we do not use the electrochemical process. However, for the electrogravimetric process, we take the use of the electrolytic reaction, that is before and after, and then we weigh the amount of the product that is formed. So hence it is called as electrogravimetry, that is the weight of the product that is formed after the electrolysis reaction. So now there are also certain terms from in this electrogravimetric analysis. So we know that what is a cell, and we also know there are two types of cell, that is a galvanic cell and an electrolytic cell. So a galvanic cell, it is also called as a voltaic cell. It converts electrical energy into chemical energy into electrical energy. But when we talk of the Daniel cell is an example of such a galvanic cell. Now, when the energy is supplied from an external source, the cell through which it flows in is called as the electrolytic cell. Now, so irrespective whether the cell is galvanic or electrolytic in nature, the electrode where oxidation takes place is always called as the anode, where reduction takes place is always called as the cathode. So we will now consider a cell of the type where copper is deposited at the cathode and oxygen is evolved at the anode. So this cell reaction is represented by this in this representation, that is Cu2 plus the salt bridge, 2H plus half O2, that is platinum electrode. So then we will consider the reaction at the cathode, and we know that the reduction always occurs at the cathode. So here the cathode reaction, it implies Cu2 plus 2E forming the with the reduction reaction Cu2 plus, it converts to Cu0 state. And in the anode reaction, here the HgO, it forms 2H plus half O2 and plus the overall, when we write the combination, this is what we get, the overall reaction. This is the combination of the cathode reaction and the anode reaction. Now the potential of the electrochemical cell, here when we want to know the potential of the electrochemical cell, then we can calculate the difference of the potential of both the electrodes, that is the potential of the E cathode minus the E anode. So this is the, that is the Hubsel potential of the cathode and anode. So once we know this, then we can calculate the potential of the total cell potential of the electrochemical cell potential, we can find out. So here in figure 5.1, a simple diagram of the electrolytic cell of the, it has been shown here. So here a voltage, that is E applied, is given here, that is it is applied to the cell. Now when this E applied is greater than the potential of the cell, then there will be a flow of current inside the circuit. Now when there is current, the potential of the cell is less than the thermodynamic potential because of one of the following phenomena, that is we called it as the IR drop, concentration polarization, or chemical polarization. So these three things are possible when there is the current flow inside the cell and the potential of the cell, it becomes less. So now here we will understand what is IR drop, or we call it as ohmic potential. Now we know from Ohm's law V is equal to IR. So here we will apply this and we will understand what is IR drop. So now the electrochemical cells, we know they also resist the flow of charge. So in both types of conduction, here we know that Ohm's law describes the effect of resistance. So here the product of the resistance R and the current I is called as the ohmic potential or the IR drop of the cells. So here we call it as I into R, that is the resistance of the cell. When it is multiplied with that of the current in amperes, that is represented as I, then the product of this I and R is called as the ohmic potential, or it is also known as the IR drop of the cell. So now we know that when we applied a potential, that is E applied, becomes equal to the cell potential, then no current it flows inside the cell. But when we gradually increase the value of the applied potential, then what happens is a small amount of current starts flowing inside the circuit. Now this current through the cell, it encounters resistance, which uh, which gives rise to the potential drop of minus IR volts. So in other words, the applied potential here, it must be greater than the theoretical cell potential by IR volts. So thus we can say the E applied has to be greater than that of the cell potential by minus IR. That is, E applied is mathematically given as E cathode minus E anode minus of the ohmic potential, that is the IR. So the above equation here in equation 5.2, we will arrange this equation and we find out that I is equal to minus E applied by R plus 1 by R of E cell. So here I can be written as E cell minus E applied by R. So when we take small amount of current and for a very small time period, the E cathode and E anode, they do not change much. So the I can now be represented as E applied by R plus K. Now this K that is represented in equation 5.4, it is a constant. Then here in figure 5.2, we see a plot of current versus potential. This is a IE curve. Here it has been shown as a function of the applied potential in a electrolytic cell. It is a straight line and the slope is equal to the negative reciprocal of the resistance, that is slope is equal to minus 1 by R. So this plot is linear with small currents. When we elaborate this curve, we see from figure 5.3a, when the current is very small, then the plot is linear. But as the voltage increases, here we can see in figure B. So here the current, there is a, we can see here it is a deviation. So this is how a galvanic cell they behave in the same way. So this is the IE curves for an electrolytic cell which is linear in nature, and for a galvanic cell which shows deviation. Now there are cells that exhibit also, they show non-linear relationship and they are said to be polarized, and the degree of polarization is given by the over voltage, or what we call it as the over potential. So here polarization, it requires the application of a potential which is greater than the theoretical value of the current. So thus an over potential of minus 0.04 volt is required to obtain a current of 0.06 ampere. So here this is how it has been calculated. Then applying the over voltage, then the equation 5.1 can be written as the E applied, it will be equal to E cell minus, here it will be equal to E cell minus the IR, that is the ohmic potential, minus the over voltage value. So this is one simple way to remember the to calculate the applied potential for the current to flow pass through the circuit. Then comes the polarization. So here we will again consider this situation here in figure 5.3a. So here in figure 5.3a, this is a IE curve, and this is for small change in current value. We see there is a linear, the current varies linearly with the potential. So this is what we have seen. Now if we increase the E applied, then after one point the current becomes independent of the E applied. So this gives rise to the case of the limiting current. Here it has been shown in figure 5.4. So here we know the graph is linear, but as we keep on increasing, then it deviates from the original value, and we see this current here after the deviation, it is called as the limiting current. So here at this situation we say that the electrode is completely polarized because its potential can be changed widely without affecting the current. So polarization has been divided into two categories, that is concentration polarization and kinetic polarization. This kinetic polarization is also called as chemical polarization. Now, polarization is an electrode phenomena which affects either or both of the electrodes. So, first, we will talk about concentration polarization. So, when ions are discharged and deposited on an electrode because of the result of passing current through it, then the area that is present immediately near the electrode is depleted of ions, and the layer it or offers resistance to the passage of the current. So this type of resistance, due to the change in concentration of the electrolyte around the electrode, it is known as concentration polarization. So here concentration polarization occurs when the ions do not arrive at the cathode or the product do not leave the anode fast enough to maintain the current gradient. Now we also know that the reactants are transported to the electrode surface by three mechanisms, that is diffusion, migration and convection. So here the concentration polarization, it arises when the effects of diffusion, migration and convection, they are insufficient to transport the ions so that the magnitude of the current can be maintained. If the depleted area in the vicinity of the electrode is not supplied with ions from the bulk of the solution, then the cathode will take up more and more negative potential when we keep on increasing the potential. So as a result, a back EMF is set up and the current has to flow through it. So here for this reason, vigorous stirring and heating are important in electrode deposition process. Then coming to chemical polarization. So chemical polarization, it occurs due to the change in the chemical nature of the electro deposited product of the metal during the process. So kinetic polarization or the chemical polarization may also be caused by the formation of films on the electrode. For example, like aluminum electrode, here when we say aluminum anode, it is liable to formation of a coating of alumina, that is alumina oxide on it. So hence this is an example of a chemical polarization where the nature of the product it increases. So kinetic polarization, it is most prominent in electrode processes that yield gaseous products. So this potential is known as overpotential. The gas overpotential depends on several factors such as electrode material, current density, temperature, pH, etc. So overpotential for many metals, they differ differently. The overvoltage at any current density, it decreases as the surface area it is increased, and this results in a current density. So hydrogen overvoltage is greatest in metals such as cadmium, lead, tin and mercury. One of the essential requirements of electrodeposition is that the deposit must be compact and very fine, and it should stick to the electrode. So simultaneous evolution of gas, it results in a very spongy and feathery deposit. So gasification here as a result, when high current densities are applied, then gasification occurs. So this gasification, they can be controlled by controlling or using suitable buffers. Now complex ions, they give very smooth deposits, like when silver deposited from silver cyanide, it gives a very smooth deposit of the silver cyanide. So why this over voltage is important? Because there are 4 points to remember. The existence of over voltage, it explains various phenomena. Suppose in a lead accumulator, during the charging, the lead is deposited on the cathode instead of the hydrogen being evolved. So due to the high over voltage of lead, it is possible to deposit electrolytically the metals which have a more negative potential than hydrogen from its acid solution because of high over voltage of hydrogen on these metals. Over voltage also plays an important role in the industrial production of chlorine and sodium hydroxide by the electrolysis of brine, that is sodium chloride solution. So when electrodes of high over voltage they are used in electrolytic reduction, it would mean to increase its reducing power. So the electrodes with high over voltage like lead, instead of platinum, they can be used in organic electroreduction processes. So these are the some of the merits of over voltage. Then coming to types of electrogravimetric methods. The electrolytic deposition or the electrolytic precipitation, they have been widely used for the determination of metals. So here the metal is deposited on a mostly on a platinum cathode, and then the increase in mass is measured. So there are two types of electrogravimetric methods. So one is the constant current electrolysis and the second is the constant potential electrolysis. So first we will talk about constant current electrolysis. So here, as the name implies, the electrodeposition is carried by keeping the current constant. So here, periodic increases in the potential are required. That is, the potential is increased periodically as the electrolysis proceeds. Then here in figure 5.5, this is the general apparatus for carrying out constant current electrolysis. Here the apparatus, it consists of a suitable cell and a direct current source. A 6-volt storage battery can be used for DC power source, an ammeter and voltmeter. That ammeter measures the current and voltmeter measures the applied voltage. So they are all controlled by a resistor. So here the cathode is usually a platinum gauge. So after deposition, we can measure the amount of the metal that is deposited on the platinum anode. Then the physical characteristics of the metal deposits that occur in the platinum anode during the electrolysis process. So here it should be important that the deposits, they should be pure and dense and smooth, and they should stick to the electrode. Spongy or very powder type deposits, they are not very acceptable in this process. So here the principal factors that influence the physical characteristics of the deposits, they are current density, temperature and the presence of complexing agents. So the stirring generally it improves the quality of the deposit. The time of deposition is reduced when the solution is stirred vigorously. This type of stirring, it lowers the concentration over potential and also enables a smooth deposit without any adverse effect. Now, during the evolution of a gas at the electrode, it is not a very desirable process when gas comes out during the deposition process. So hence it should be taken care. If there is a gas evolving, then spongy deposits are obtained, so which is not required. The chemical nature of the ion in solution also has an important influence on the physical form of the deposit. So for example, a pure and bright deposit of copper, it can be obtained by electrolyzing a nitric acid solution of cupric ions. So in contrast, a coarse tree-like deposit of silver is got under similar conditions. The electrolysis from a solution of silver cyanide, it produces a very good deposit. And also, increase in temperature, it favors the diffusion process, but the hydrogen over potential is decreased and the stability of many complex ions is decreased. Then coming to the potential changes during electrolysis at constant applied potential. Now let us consider the electrolysis of Cu2 plus ion in acidic medium. That is, here it is shown in figure 5.6. So initially the applied potential to the cell is about minus 2.5 volt, which leads to a current of about 1.5 amperes as shown here. It is shown in figure 5.6a. So as the electrolytic deposition is copper is completed at this potential, the IR, that is the ohmic potential or the IR drop, it decreases continually. This decrease is due to the concentration polarization that occurs at the cathode. Now, this decrease in IR, it must be compensated by some increase in cathode potential because the cell potential remains constant. So, if the ohmic potential drops, then there must be another factor which will be increasing. So, here this increase in potential is slowed down at point B. Here it is in this point B. Here it is shown by the reduction of hydrogen ions. Then, since the solution now contains a large excess of acid, the current is no longer limited by the concentration polarization, and hydrogen goes on simultaneously until all the copper ions are deposited. So here, under this condition, the cathode is said to be depolarized by hydrogen ions. Then again, we will consider a case which contains both Cu2 plus and Pb2 plus. Like here in this case, here we have seen in figure 5.6b. So if we have a mixture of two ions, then the co-deposition of hydrogen occurs in such type of electrolysis and very spongy deposits are formed. So thus, for such cases which contains two types of ion, there are depolarizers are used to maintain the efficiency of this process. So here the copper that is deposited, it is more smoother, it is smoother in nature, and the because the nitrate ions, they act as the cathodic depolarizer and prevent the evolution of hydrogen. So nitrate ions have been used in the constant current deposition of copper since a very long time, because the nitrate ions, they help in the quantitative deposition of cupric ions at the cathode and prevent the formation of the metallic Pb at the cathode. So these are some of the typical applications here in table 5.1 of constant current electrolysis. Like for example, the analyte is silver plus, it is weighed as Ag. The electrodes are platinum electrodes, and the conditions they have taken is alkaline cyanide solution. So here some of the applications have been given for constant current electrolysis. Then now we will talk about constant potential electrolysis. So as the name implies, here the potential remains constant. So when by keeping the potential constant, it is possible to separate two elements whose deposition potentials it differ sufficiently. So the potential of the cathode is controlled so that it never becomes sufficiently negative to allow for the deposition of the next element. So here, as we have seen from above figure, the potential of the cathode, it becomes negative due to concentration polarization, and that the co-precipitation or the co-deposition of the species begins. So a large negative drift here, it be avoided in such type of systems when you have a three electrode system. Here is the figure, the controlled potential apparatus, electrolysis apparatus. Here it is shown in figure 5.7. So from this figure, we see it consists of two independent electrode circuits that share a common electrode, the working electrode at which the analyte is deposited. The electrolysis circuit, it consists of a DC source, a potential divider, and the working electrode, a counter electrode. The reference is the generally SCE, that is the standard calomel electrode, a high resistance digital voltmeter, and a working electrode. So the current in the reference electrode circuit is zero. It is maintained zero at all times. So the purpose of the reference circuit is to monitor continuously the potential between the working electrode and the reference electrode. So when this potential reaches a point at which deposition of an interfering species begins, then the potential across the working and counter electrode is decreased by moving contact C to the left. So here in figure 5.7, we can see the change in cell potential and current during a controlled cathode potential of copper C. This is the process controlled cathode potential electrolysis of copper, and here this technique usually demands constant attention because this is a very sensitive process and it requires constant attention during the operation. Then most for such type of electrolysis, we the electrodes are mostly used are the platinum gauge electrodes, because they have the advantage of being non-reactive, and they can be ignited to remove any organic matter that has been deposited. So certain metals like bismuth and zinc, they cannot be deposited directly on platinum because they cause damage to the platinum electrode. Hence, a protective coating of copper is always deposited on the platinum electrode. We also have mercury cathode. Mercury cathode is particularly useful for removing easily reducing metals as a preliminary step. Here in figure 5.9, a mercury cathode for the electrolytic removal of ions from solution has been shown. For example, copper, nickel, cobalt, silver, and cadmium. They are readily separated at this electrode from ions such as aluminium, titanium, the alkali metals, sulfates, and phosphates. The precipitated elements, they dissolve in mercury with little hydrogen evolution because mercury has a high hydrogen over voltage, and hence no hydrogen evolution occurs even at high applied potentials. The advantages of mercury cathode is that it forms an amalgam with a number of metals. It has a high hydrogen over voltage and no hydrogen occurs even at high potential. The application is that the controlled cathode potential is very useful in the separation of quantitative determination of metallic species, that is successive deposition of the metals. Suppose we take a mixture of copper, bismuth, lead, cadmium, zinc, and tin, and they can be determined by the successive deposition on the platinum cathode. First, copper, it is deposited by maintaining the cathode potential at minus zero point 0.2 volt versus the standard calomel electrode. So after weighing the cathode, the copper plated cathode is used to deposit bismuth at a potential of minus 0.4 volt. Then lead is deposited over the same cathode by maintaining a cathodic potential of minus zero point 0.6 volt. All these three elements, they are deposited from a neutral solution that contains tartarate ions, which forms complexes with tin and prevents its deposition. Now when lead deposition is completed, the solution is made strongly ammoniacal, and zinc and cadmium, they are separated. Finally, this solution is acidified to decompose the tin tartarate complex using a potential of 0.065 volts. So this is how we can use this constant potential electrolysis for successive deposition of metals. Then there is also the possibility of simultaneous deposition. So a mixture of copper and lead, they can be determined by the deposition of copper in the presence of nitrate, because here the lead, it can be deposited as lead dioxide. So hence simultaneous deduction of metals is also possible. Then it is also used in preparative organic chemistry. Like if there is any organic compound which undergoes a series of reduction or oxidation, each at a particular potential, then it is possible to reduce the starting material to the desired product by controlling the potential of the cathode during the reaction. So here in table 5.2, the applications of controlled cathode potential electrolysis has been tabulated. So here we can see if the analyte is Cu2 plus, platinum cathode is taken, and the electrolytic solution is H2SO4 and HNO3 solution. Similarly, other analytes and their particular conditions have been maintained here. It has been mentioned here in table 5.2. Now coming to coulometry. So coulometry, these methods, the measurement of coulometry or the coulometric methods, they are based on the quantity of the electric charge that passes through the solution during the electrochemical reaction. The principle of coulometric method, it is mostly governed by Faraday's laws. So first we will study what are the Faraday's laws of electrolysis. So first is the first law of electrolysis. So according to this law, the mass of a substance that is liberated at the electrodes during the electrical electrolysis is directly proportional to Q that passed through the electrolyte. That is, if M is the mass of the substance, current is I and T in second, then according to first law, M is directly proportional to T, or M is directly proportional to I into T. Here M is equal to Z into I into T, where Z is the proportionality constant. So here we see that the first law, it relates the quantity of current, that is q, and the extent of the chemical change that can take place. Now the Faraday's second law of electrolysis, it states that the mass of different substances that are either evolved or deposited by the passage of same quantity of electricity, that is directly proportional to their chemical weights. That is, small m is directly proportional to the equivalent weight of the substance. The equivalent weight is given as capital M, that is the molar mass of the substance, and N is the valency of the ions of the substance. So here, if we have M1 and M2 of two different masses, and they are capital M and capital M2, they are the respective molar masses, then according to this law, we have M1 by M1 is equal to M2 N2 by capital N2. So that is, for example, if we, what we mean from this law is that if we take copper sulfate and AgNO3, then from the second law we get mass of the copper deposited by mass of molar mass of copper into 2 is equal to mass of the silver deposited by molar mass of silver, because here into 2 is multiplied looking at the valency of the metal, and here is 1 for the valency of the copper, sorry, of silver. Then the quantity of electric charge, it is equal to the product of strength or the current and time, that is q is equal to I and t, and the practical unit of electricity is coulomb. So when a current of 2 amperes, it flows for 10 seconds, then q is equal to 2 into 10, that is 2 amperes into 10 seconds, that is 20 C. Capital C indicates the coulomb. So here, for a variable current, I indicates the electricity. Now we will define the term, that is Faraday. So what is this Faraday? Here, the quantity of electricity which is carried by 1 mole of electrons is called Faraday, and it is given the symbol capital F. Now we know that the charge on one electron is 1.6 into 10 to the power minus 19 mu. So the charge on 1 mole electrons will be 1.6 into 10 to the power minus 19 into the Avogadro's number, which gives us the value 96490, or this has been approximately used as 96500 coulomb. So 1 Faraday becomes 96,500 coulombs. So now we will consider a normal reaction that is given in equation 5.1, that is M n plus, it takes up n number of electrons to form the metallic ion, that is capital N. So the quantity of electricity required for the deposition of 1 mole of the element will be equal to N into F. So that is, for the deposition of 1 mole of the substance, we require NF, that is N into 96,500 coulomb. So here the small m, that is the mass that can be of the substance that is deposited, it can be given as capital M, where it is the atomic mass of the molar mass. Q is, we can calculate here the coulomb, and the 96500 into small n. So this, simplifying this above equation, we get small m value to be this, and here this equation is very useful in calculation of the quantity of the current for a electrolysis process, this equation in 5.13. Then coming to coulometer. So coulometer, the quantity of electricity is that is required to change the chemical nature of the substance is measured by an instrument, and that is called as a coulometer. So in practice, it is, it ammeter is actually substituted with the coulometer. So each coulometer is a second electrolytic cell in which anode and cathode, they may be in the same compartment, and it is expected to proceed at 100% efficiency. So various types of coulometers like gasometric coulometer, hydrogen oxygen coulometer, gravimetric coulometers, silver coulometer, titrimetric coulometer, and iodine coulometers, they are in use. So we'll first start with gasometric coulometers or hydrogen oxygen coulometer. So it consists of a glass tube like approximately 50 centimeter long. Here in figure 10 it has been shown the diameter is 2 centimeter. Two platinum sheets of about 1.5 square centimeter. They are joined with a stout platinum wire that serve as the electrodes. So calibrated tube is connected to the electrolysis tube by means of a pressure rubber tube, and it is capable of moving vertically. So a zero point 0.5 molar solution of potassium sulfate, here it is used as the electrolyte. So upon electrolysis, the following reactions occur. So at the anode, OH minus is converted to H2O and O2 is liberated, and at the cathode, H2 is liberated. So overall reaction, it is obtained by combining the above cathodic and anodic reactions. So here we see 3 moles of gases, that is 2 mole of hydrogen and 1 mole of oxygen. From the above equation we see they are produced by consumption of 4 faradays of electricity, so which is equivalent to 0.1 liters of NTP, or at NTP of mixed gas per coulomb. So such coulometers, they are highly accurate in nature, and it has also they because since they are very accurate, they also have been used for measurement of current density. It has been reported that the loss of efficiency is due to the formation of hydrogen peroxide at the anode. So here when we the common other common gasometric coulometer is the hydrogen nitrogen coulometer. So here zero point 0.1 molar hydrogen sulfate is used as the electrolyte. So at the anode, N2H5 plus is converted and nitrogen is related, whereas liberated, where at the cathode H2 is liberated. So when we combine this equation, we see 3 moles of gas are produced. 1 mole of N2 and 2 moles of H2 are produced, and 4 faradays of electricity has been consumed. So this is how these coulometers are used. There need to be followed certain precautions that while handling such type of coulometers. The first is that the gas burette, it should be water jacketed, and the temperature, it should be within the scale of plus minus zero point 0.1 degree centigrade. The electrolyte must be pre-saturated with oxygen and hydrogen mixture, and during the course of the reaction, the gas burette must be lowered periodically to hold the gas pressure close to atmospheric pressure to maintain a equilibrium. Then now coming to a second type of coulometer, that is your silver coulometer. So it is an example of a gravimetric coulometer in which the amount of the metal that is deposited at the cathode or the amount of metal stripped from an anode is determined. So here in figure 5.11 we see the generally schematic diagram of a silver coulometer. So here in this case it consists of a platinum disc or a silver disc which acts as the cathode, and it contains 1 molar of silver nitrate. Okay, so we were discussing this silver electrode. So here in this case, the uh, Yes, so we were talking about the current density. It should not exceed zero point 0.2 ampere per centimeter square. After electrolysis, the cathode it should be taken and dried. So the increase in the mass of the cathode it gives the amount of silver that is deposited. Then also we have iodine coulometer. This iodine coulometer is an example of a titration coulometer in which anodically generated iodine it is titrated with thiosulfate or arsenic solution. So this has been used in the determination of Faraday constant. Then we also have colorimetric coulometers, so which are based on the principle of developing colored species upon the reaction with a reagent and the metal. So as a colored species is developed, then if the metal ion may be cathodically reduced and the absorbance it can be measured. Example is reduction of iron at the cathode and measuring its absorbance as 110 phenanthrolene reagent. Then we have radioactive coulometers. So here a microcoulometer that is based on the counting deposits of silver 110, that is a radioactive element, it has been described. So here radioactive silver is known for with an is spiked with an unknown silver solution, and then the electrolysis is made. So equal amounts of silver they are plated on the each cathode. Then after the electrolysis process we can measure the amount of silver that is deposited and the amount of radioactive silver that is changed. So here the measurement it involves the ratio of the radioactivities of the two cells. So from this measurement we can calculate the our metal estimation. Then the types of coulometric methods. So in general, coulometric methods have been classified into two types, that is amperostatic where constant current and controlled potential, that is potentiostatic. Now this amperostatic coulometry they have been classified into primary coulometric analysis and secondary coulometric analysis. This controlled potential coulometry or the potentiometric coulometry, potentiostatic, it just consists of coulometric titration. The secondary coulometric analysis, it is further divided into external generation and internal generation. So two general techniques that can be generalized for coulometric analysis are constant current, that is amperostatic, and controlled potential, that is potentiostatic coulometry. So first we will talk about constant current coulometry. So here the current is maintained constant till the completion of the reaction. So the quantity of electricity that is required to achieve the end point is derived from the amount of coulombs that is consumed by applying the Faraday's laws. So the primary constant current coulometry, in this technique the element it undergoes direct reaction at the electrode with 100% efficiency. Then we have secondary constant current coulometry. This is more frequently used and it is called as coulometric titration. So here one of the reactants, it is quantitatively generated at the electrode which then reacts with the analyte that has to be estimated. So a titration of ferric ion, that is Fe2 plus versus ferrous ion, that is Fe2 plus versus ferric ion, it is an example of a coulometric titration. So here coulometric titrations they are more popular because of the in situ generation of the titrimetric reagents. Then coming to potentiostatic coulometry. So here the potential is of the cell it remains constant, so that the oxidation or reduction of the changes in the analyte it occurs. The current is initially high but it decreases rapidly and it approaches zero. So then special features of the coulometric methods. So coulometric methods, they give more accurate and precise results than classical measurements. These methods, they are suited for both routine analysis and rare analysis. Coulometric titrations, they are more popular and they have the special advantage because of their storing and handling process. The titrations which cannot be performed by conventional methods, they can be easily performed with coulometric process. There is in situ generation of titrants, so which helps in easier estimation of organic substances like oxime and others. Constant current coulometry has been widely used than controlled potential coulometry because that is amperostatic coulometry is a faster process and requires very simple instrumentation, and constant potential coulometry is very sensitive and has very high selectivity. So then we will talk about potentiostatic coulometry. So in potentiostatic coulometry, the potential of the working electrode, it is held constant. This technique is similar to electrogravimetric process. Hence, the control potential technique, it can be applied to systems that yield very high deposits. The instrumentation for this process, it consists of a potentiostat, a electrolysis cell, and a chemical coulometer. So the chemical coulometer mostly is the hydrogen oxygen coulometer or the silver coulometer, they can be used. So here figure 5.12, you can see the electrolysis cell for potentiostatic coulometry. So the cell assembly mostly contains of a platinum gauge working electrode, a platinum wire counter electrode, and a SCE as the reference electrode. So the counter electrode is separated from the test solution by a porous tube that contains the same supporting electrolyte. So here figure 5.12, here it has been shown. Sometimes mercury cathode is also used instead of the platinum electrode, and here it has been shown in figure 5.12b. Then coming to potentiostat. A potentiostat is an electronic device which maintains the working potential of the working electrode at a constant level. So here figure 5.13, here this is an example of a potentiostat. Here if we consider this circuit 5.13a, then we see there are two resistors in the diagram. So Rs, it indicates the resistance of the counter electrode, and Ru is the unknown cell resistance. So here, because of the very high resistance between the input and the operational amplifier, there is no current in the feedback loop to the inverting loop. So if we consider the path between the inverting input and the current and the circuit output, then we see here E2 is equal to E1 is equal to ESCE plus EC, where EC represents the cathode potential. So during electrolysis, if the Ru, the resistance of U and S changes, then we have to maintain in such a way, the amplifier must be maintained in such a way so as to we get EC is equal to IC into Ru. So here the practical circuit that is shown in figure 5.13c, here it shows other components of potentiostatic coulometry. The circuit, it includes a variable voltage source at the non-inverting input. Then coming to integrators. Most of the modern apparatus for potentiostatic coulometry, they employ integrators. Now, efficient stirring is one of the conditions for potential electrolysis. Besides stirring, the ratio of the electrode surface to solution volume is another requirement. That is, the ratio, it plays an important role. We have I is directly proportional to C into A. We know Q is equal to I into T. So Q is equal to I into T, which is directly proportional to C into A into T. Then coming to applications of controlled potential electrolysis. So first in the inorganic analysis. Here the controlled potential methods, they have been coulometric methods, they have been used widely in the estimation of different metal ions. Almost 55 elements of the periodic table, they have been identified from this process. Then coming to analysis of radioactive materials. This technique is widely adopted for the determination of uranium and plutonium, and hence it finds very much use in the field of nuclear energy. Third is the microanalysis. Controlled potential coulometry is more popular than the electrogravimetric methods because it avoids the final step of weighing the product. The tedious process of drying and weighing the electrode after each electrolysis is also avoided. So this technique is especially useful for the determination of small amounts of analyte even with an accuracy of plus minus 0.5%. Then coming to multi-step control potential electrolysis. So determination of several metal ions in the same solution is also possible with controlled potential electrolysis. So here a sample solution that contains different types of metal ions such as Cu2 plus, bismuth 3 plus, lead 2 plus and Zn2 plus, they can be analyzed by this process. When the cathode potential is controlled to a plus 0.008 volt versus the SCE, then the Cu2 plus, it is reduced to copper 0. Now when the current comes to 0, then the potential can be controlled so that Bi3 plus also becomes Bi0. Subsequently, by controlling the potentials, Pb2 plus can be determined as Pb0 and Zn2 plus as Zn. So here a sample of brass bronze which contains copper, zinc and lead, they can be analyzed by this technique. Now coming to continuous monitoring of gas streams. So determination of trace level concentration of oxygen in a gas stream, they can be done by controlled potential analysis. The cell consists of a porous silver cathode and a cadmium anode. The reactions are O2 plus H2O giving rise to 4OH minus and cadmium giving rise to cadmium hydroxide at the anode. So the porous silver cathode, it serves to break up the incoming gas into small bubbles wherein the reduction of oxygen, it takes place quantitatively within the pores. The hydroxyl ions formed during the reduction, it reacts with the cadmium anode and forms a CdOH whole 2 product. Here in figure 5.14, we see an instrument for continuously recording the oxygen content of a gas stream. So a special feature for particularly is this setup is that the galvanic cell is formed and hence no external power supply is needed. There is no need of a potentiostat to control the potential of the working electrode. The current produced, it is passed through the standard resistor and the potential drop is recorded. The oxygen concentration is proportional to this potential and it can be studied from the digital display. Then another use is electrolytic determination of organic compounds. Controlled potential coulometry, it offers a new step for electrolytic determination of organic compounds. Like for this purpose, trichloroacetic acid and picric acid, they are quantitatively reduced as a mercuric electrode and they have been accurately analyzed at an accuracy of 0.1%. Then electrolytic synthesis of new compounds. Even new chemical compounds have been possible. Synthesis of new compounds have been possible. No chemical reagents are needed because the electrons can carry the reagent for carrying out the reaction. Even no contamination also occurs by this process. Then determination of n values. So this the n values, it offers a route to understand the kinetics and mechanisms of the reaction. Now, picric acid is reduced at mercury cool cathode to which n value has been found to be 18. Thus, the reaction can be identified like this. So, once we know the n value from coulometry, we can also predict the reaction kinetics and mechanism. So, these are some of the applications of controlled potential electrolysis. So, now coming to amperostatic coulometry. So here this process is known as coulometric titration. So here the a titrant, that is generally it reacts stoichiometrically with another and it almost proceeds with 100% efficacy. So here is a in figure 5.5, it represents a schematic of a coulometric titration. This is a typical coulometric titrator. The cell assembly, here it consists of a generator electrode at which the titrant is generated and a counter electrode to complete the circuit. Here it is the typical coulometric titration cell. So the generator electrode is a platinum foil or a gauge with a large surface area. The products formed at the secondary electrode, it normally interferes with the electrochemical reaction. For example, the anodic generation of oxidizing agents, that is, it is mostly accompanied by the evolution of hydrogen. Now this hydrogen, it reacts with the oxidizing agent and leads to a positive error. Hence the electrode is isolated from the test solution by a sintered glass. the external generation of titrant. Since internal generation of titrant sometimes interferes with the solution, it becomes necessary to generate the titrant externally. For example, the hydrogen and hydroxyl ions, they are produced by the electrolysis of sodium sulfate solution. Here, at the cathode, H2 is generated. At the anode, we see the H2O, the O2 is generated here. So here the cell consists of two electrodes of platinum gauge which are separated by a sintered glass. So this type of external generation apparatus has been used for the generation of other reagents such as iodine by the oxidation of anode and etc. Then detection of endpoints in amperometric titrations. So here it is very easy. Detection of endpoints with starch indication in titration, they can be more accurately determined by the coulometric or such as potentiometric, conductometric. Here potentiometric endpoint detection, it has been very found suitable to be acidimetric and redox titration. Now the advantage is that the titrations can be stopped exactly at that point. So thus these methods, they are more advantageous. So amperometric detection of endpoint, it is useful in redox and precipitation titrations, and it is more advantageous than potentiometric titration. So spectrophotometric endpoint detection has been developed, and in recent years this is of great importance. Some of the special advantages are the exact endpoint, it can be determined by extrapolation of the linear portion of the plot before and after the endpoint, and by proper choice of lambda max and molar absorptivity. So the sensitivity and selectivity of the methods, it can be improved. Now coming to the applications of coulometric titration. So coulometric titrations, they have been developed for volumetric titrations. Some of the important applications are, the first is the neutralization titration. So here the titration of strong acid or weak acid with hydroxide ion generated at the cathode have been developed. So here we see, for this reaction, the endpoints can be detected by the use of indicator. However, potentiometric endpoints, they can also be employed during the, depending upon the availability of the instruments. It is necessary to first de-aerate the solution before the analysis. So here the cathode must be isolated to prevent the interference of the hydroxide ions with the electrode. Then coming to precipitation and complex formation titrations. So a large number of coulometric titrations have been developed with anodic generation of silver ions. This generator electrode, it consists of a heavy silver ion, and the endpoints, they have been detected with adsorption indicators. Now complexometric titrations using diethylene diamine tetraacetate ions have also been developed for the titration of several cations. The reduction of amine mercury EDTA chelate has also been studied to know the complexation processes. Then coming to oxidation reduction titrations. The oxidizing agents such as iodine, bromine, fluorine, and the unusual oxidation states of certain ions like silver 2 plus, manganese 3 plus, and uranium 4 plus can be generated from such coulometric methods. Here in table 5.3, we can see some of the applications of these reagents. Here for mercaptans, here we can see the generator of the electrode and the analytical reaction they have been used. Coulometric titrations, they are important because coulometric titrations of these redox reactions, they are important because of the possibility of in situ generation of unstable reagents. So the conventional volumetric analysis cannot prepare these reagents. So the electrochemically generated these reagents, they cannot be used in conventional coulometry. So here in table 5.4, there is the applications of the coulometric titrations that involve redox reactions. Now coming to advantages of coulometric titration. So the preparation, standardization and storage of standard solutions, they are not necessary in coulometric titrations. It is easy to handle small quantity of reagents. The single constant current source can be used to generate precipitating, complexing and redox reagents. Coulometric titrations can readily be adapted to automatic titrations as the current control is easily done. A number of automatic coulometric titrators they are available in the market. In chloride titrator, silver ion is generated coulometrically. In sulfur dioxide monitors, anodically generated bromine oxidizes the analyte to sulfate ions. In water titrators, Carl-Fisher reagent has been used electrolytically to determine the trace level of water or moisture. So here in summary, the concepts of gravimetry and coulometry, electrocoulometry has been discussed, and the various types of and their applications, the techniques, it has been discussed here in this unit. So now we'll just take a break of 5 minutes and then again continue with our next unit, that is the applications of coulometry and gravimetry. So now we'll start with the second unit that concerns with the applications of conductometry, electrogravimetry and coulometry. So here some problems are given which we will also discuss. So first we'll start with the applications of conductometry. So conductometry has mostly been used for the calculation of the degree of dissociation or the endpoints of various uh, weak acids, bases, and titration reactions. So first we will talk about the degree of calculation of degree of dissociation of weak electrolyte and its dissociation constant. The conductivity values, they can be used for calculating the degree of dissociation. So let us consider here in equation 6.1 a very weak acid, that is Ha, which is in equilibrium with H plus and A minus. So at the equilibrium concentration, the concentration of Ha will be C into 1 minus alpha. This is C alpha and A is also C alpha. So we know alpha is the degree of dissociation or the degree of ionization. So if we write the thermodynamic constant Ka, it can be written as activity of H plus into activity of A minus by activity of Ha, or that is in terms of concentration we can write it as H plus into A minus by concentration of Ha. Now we from equation 6.1 we see that the concentration of Ha is equal to C into 1 minus alpha and H plus and A minus it is C alpha. So substituting these values we get K is equal to alpha square C by 1 minus alpha. This equation is called as Ostwald's dilution law and this is for a weak acid, the calculation of the dissociation constant of a weak acid. Now similarly for a weak base we can take Kb, that is the dissociation constant of the base, and it can be written as Kb is equal to alpha square C by 1 minus alpha. So these Ka and Kb, they indicate the Ostwald's dilution law or the dissociation constant for a weak acid and a weak base. So now we will consider the partial dissolution of a salt Ma, which is very low solubility. So here the equilibrium constant for this reaction in equation 6.7, it can be written as Ks, that is the dissociation constant of the salt, is equal to concentration of the H plus, M plus and concentration of A minus and the concentration of Ma. Now we know the Ma is a salt and its concentration can be the activity or concentration can be written as 1. So here this Ks, it becomes concentration of M plus and concentration of A minus. So now this is K here. It is also called as the solubility product. Now we will derive a relationship between the molar conductivity and the limiting molar conductivity. So here we know lambda m is equal to alpha into lambda to the power infinity, or we can write alpha is equal to lambda m by lambda infinity, and this relationship is called as Ostwald's relation. So substituting this value in Ka, we can find out the dissociation constant of acid, the Ka, can be written as alpha m by alpha infinity whole square into C by 1 minus lambda m by lambda to the power infinity. So here when we rearrange this equation, we get the equation that is similar to figure equation 6.12. Now when we plot a graph of lambda m versus lambda m into C versus 1 by lambda m, then we get a linear plot where the slope gives us the value of Ka. Therefore, from the plot, we can know the value of Ka. Now here in table 6.1, various the molar conductivity of nitric acid in methanol in different concentration, it has been shown here. And here figure 6.1, it shows the plot of lambda m by C versus 1 by lambda m, which is a straight line and the slope of which gives the value of the Ka. But when in the case of weak electrolytes, it is not possible to obtain the limiting molar conductivity value. So here we have to, for the weak electrolytes, we have to use the Coleridge's law of independent migration. So this law like Colrat's law, if we look into this, that is lambda infinity for acetic acid, it can be written as lambda infinity for sodium acetate plus lambda infinity of HCl minus lambda infinity of NaCl. So it cancels out and it gives us the value of lambda infinity of acetic acid. So the values of molar conductivity at infinite dilution for sodium ethanoate, here it has been one example has been shown, and how we can calculate the lambda infinity values. This is also an example depicting the calculation of Ka. Now coming to the ionic product of water. So when water contains, we know the ionic product of water is given by the formula Kw is equal to concentration of H plus and concentration of OH minus. Now we know Kw is called as the ionic product. So how can we determine this Kw from conductivity measurements? So if the concentration of ionized water is C, that is C of H plus is equal to C of OH minus is equal to C. So the equation here 4.8, we can calculate lambda m is equal to kappa, or C is equal to K by lambda infinity of H plus and lambda infinity of OH minus. Thus the conductivity of pure water, it has been found to be 5.8 into 10 to the power minus 6 Siemens per meter at 298 K. We will substitute this value in equation 6.12 here in 1,4, and then we find out the value, the Kw has, by this method we can find out Kw comes to be 1.12 into 10 to the power minus 14. So here this table 6.2, it shows the different ionic product and conductivity of water in different temperature, the K and Kw. Then measurement of solubility and solubility product of a sparingly soluble salt. The conductivity of a saturated solution of a sparingly soluble salt, it can be determined by measuring by the kappa of the solution minus the kappa of the solvent. So here we know that the molar conductivity of the salt, that is lambda salt, can be written as kappa salt by its concentration. Now here, since the salt is very sparingly soluble in water, we can write lambda salt is equal to lambda infinity of salt is equal to lambda infinity of the cation and lambda infinity of the anion. So that is C here. Now it becomes kappa of the salt by lambda infinity of cation by lambda infinity of the anion. So here ultimately the limiting ionic conductivities, it can be obtained from literature, and the solubility of C here we can find out. So once we know the solubility product, once we know the C, then the solubility product can be calculated. So here one example has been shown for AgCl. So for AgCl, the lambda infinity plus and the lambda infinity minus, it has been shown. The conductivity, that is the kappa value, it has also been given here. Then the first we have to calculate the concentration of Ag plus and Cl minus. So C is equal to kappa of AgCl, that is 2.28 into 10 to the power minus 4 by lambda of Ag plus and Cl minus. Here both the values have been given. So once we know the C, then we will find out the Ks. So Ks for this reaction is concentration of Ag plus and concentration of Cl minus. So here for AgCl, this becomes 2C. Then the Ksp, that is the solubility product, is equal to C square. The value of obtained is 1.6 into 10 to the power minus 5 whole square. So here we can calculate the Ksp using the conductometric values. Then coming to conductometric titrations. So here conductometric titration, the principle is based on the fact that during the titration, one of the ions, it is replaced by the other, and invariably these two ions, they differ in their ionic conductivity. So in order to reduce the influence of errors, then the angle between the two branches of the titration curve, it should be as small as possible. Here in figure 6.2, it has been shown the angle should be as low as possible. So the smaller the conductivity of the ion, then the more accurate will be the result. The larger the conductivity of the ion, then the more accurate is the angle of titration curve. The main advantages to conductometric titrations is that they are applicable to very dilute solutions. So here the application lies in acid-base titration and even at very trace levels. So some typical conductometric titration curves has been described. So first is the titration of a strong acid versus a strong base, that is HCl versus NaOH. So before NaOH is added, the conductance is very high because free H plus ion is present in the solution. Now when H base is added, the conductance falls because H plus now reacts with the OH minus from the base and the mobility, it forms H2O. So this decrease continues till we get the equivalence point, that is here. At the equivalence point, the solution contains NaCl. After the equivalence point, the conductance increases because of the large conductivity of the OH minus ions. So hence, it first decreases and then it increases. Then coming to conductometric titration of a strong base, that is of a strong base with a weak acid, that is NaOH versus acetic acid. So here the conductance first is very low because acetic acid is very poorly ionized. So when we add the base, there is increase in there is a decrease in conductance, not only due to replacement of H plus by Na plus, but also the depression is suppressed because of the common ion effect. Hence, after even adding NaOH, the undissociated is the strong, the undissociated CH3COO to CH3CONA, it is a strong electrolyte. So this increases the conductance and it rises up beyond the equivalence point. The conductance increases more rapidly. So then coming to titration of sulfuric acid with dilute ammonia. So here first the conductance is very high. Then it decreases because the replacement of H plus. But you see after the end point has reached, the graph does not change because excess ammonia is not appreciably ionized in the presence of ammonium sulfate. Then coming to conductometric titration of a weak acid with a weak base. So the nature of the curve before the equivalence point, it is similar to that of the curve obtained by titrating weak acid against a strong base. So after the equivalence point is reached, the conductance remains same as the weak acid. So and hence it does not change. Then coming to a conductometric titration of a mixture of strong acid and a weak acid versus a strong base or a weak base here. So in this curve, such type of titration, there are two breakpoints. So one breakpoint is here and the other breakpoint is here. There are two breakpoints. So the first breakpoint, it corresponds to the neutralization of the strong acid. Now when the strong acid has completely been neutralized, then the weak acid starts neutralization. So the second breakpoint is the neutralization of weak acid. So however, when the titrant is a weak base, it remains almost constant for NaOH. But if it is NaOH, then it increases. Then coming to displacement titrations. When we take a salt of a weak acid, it is titrated against a strong acid, then the anion of the weak acid is replaced by the strong acid and the weak acid is liberated from the undissociated ion. So here in figure 6.7, you can see the conductometric titration of a salt. Here sodium acetate versus HCl, here it goes like this. And for ammonia and versus NaOH, deviation here is less. The displacement is caused by the ammonium ion here. It is greater conductivity by the sodium ion, which has a very lower conductivity. Then coming to precipitation titration and complex formation titration reactions. So a reaction may be made on the basis of a conductometric precipitation titration, provided that the reaction product is sparingly soluble or is a very stable complex. The solubility of the precipitate must be less than 5%. The addition of ethanol is done sometimes to reduce the solubility of the precipitations. So an experimental curve here is given in figure 6.8. Here, this is the example of a precipitation titration here. So the this is the Titration of ammonium sulfate in aqueous ethanol solution with barium acetate. Ammonium sulfate versus barium acetate. Now, if the solubility of the precipitate was very small, then the conductance at the equivalence point should be given by AB and not observed by AC. Here, it should be given by AB and not by AC. But the addition of excess of the reagent, it depresses the solubility of the precipitate, and if the solubility is not too large, then the position of the B can be determined by stretching the two arms points of the two arms until they intersect. So a slow rate of precipitation is observed when with microcrystalline precipitate. Then coming to oxidation reduction or redox titration. The conductometric method is not very well suited for redox titrations. Almost all such reactions, they must be carried out in presence of a large excess of acid or base, and thus therefore the accuracy of the titration it decreases. So hence this type of reactions is redox reactions is not usually performed by such type of conductometric methods. Then now coming to application of electrogravimetry. So there are, we know, two types of electrogravimetry. One is constant current electrolysis and the other is constant potential electrolysis. So here in constant current electrolysis, the electrodeposition is carried out by keeping the current constant and the applied potential is increased gradually. So the apparatus for constant current technique, it consists of a 6-volt battery as the power source, an emitter and voltmeter. Emitter measures current, voltmeter measures the voltage. The voltage applied to the electrolytic cell is controlled with a resistor. So here the voltage, the here the voltage it is it is the the voltage is meant to the electrolytic cell is controlled with a resistor. The cathode is usually a platinum gauge, and the setup we have already studied. For constant potential electrolysis, this is also called as potentiostatic method. This method. So in this method, the potential of the working electrode is maintained at a constant level versus the standard calomet electrode. We have also studied the technique here. Though these techniques, they are simple, but the sensitivity is the issue in these methods are very limited. Another limitation with these techniques is the washing and drying of the electrode. So thus electrogravimetric methods are limited to detection of metals which can give very smooth deposits. The physical characteristics of a deposit, it depends on the form of the metal ion in the solution. For example, brighter deposits can be obtained in silver cyanide in nitrate medium. So both constant current and constant potential electrogravimetrics, they have their wide applications. So first is in quantitative analysis. Similar to gravimetric methods, these electrogravimetric methods are also very accurate and they involve the weighing of the product before and after the electrolysis process. So this technique has been used in determination of metal from their mixture using successive deposition. For example, electrogravimetric methods, they are used in the analysis of copper based alloys. By careful control of the cathode potential, the pH and the concentration of the complexing agents, they can be successfully deposited. Like for example, the electrolysis at minus 30 volt of a minus 0.3 volt of a solution containing 0.25 mole tartarate, it deposits copper. Further reduction at the same solution, it deposits bismuth, and at minus 60, lead is deposited. So we see successive deposition of the metals, they can be done by this process. Like any other gravimetry method, electrogravimetry, it works well when that is accurately they are weighed in the sample. Thus, this technique is not very much helpful for the analysis of trace metals. So, in table 6.2 and 3, common metals that can be determined by electrogravimetry have been listed. So, here in table 6.3, metals like Ag plus Br minus, cadmium 2 plus, copper 2 plus, Mn 2 plus, nickel 2 plus, Pb 2 plus, and zinc 2 plus. They can be measured by constant current electrolysis. While on the other hands, metals like Ag0, copper 0, bismuth, antimony, tin, lead, cadmium, and nickel, they can be estimated by constant potential electrolysis. Then coming to separations. Electrogravimetry, it has been used to separate one species from other by selectively plating it out and removing it from solution. This method is used to remove unwanted interferences that occur during the electrochemical reaction. Also, electro they have been electrogravimetry have been used to analyze the mixture of copper and lead in the presence of nitrate ions at the cathode. And electrogravimetry has also been used in preparative organic chemistry towards the preparation of a number of new organic specimens. Then coming to application of coulometry. So the basic relationship that is used in calculating the amount of substance, here we know it has been given by small m is equal to capital M into Q by 96500 into T. Here it has been given, and basically coulometry is is of two types, and it is also similar to that of electrogravimetry. So the processes are coulometry with controlled potential and coulometry with constant current. So here the coulometry at constant potential, the efficiency is almost 100%. So the completion of the reaction, here it is indicated by the current that decreases to almost zero, and the amount of substance that is produced is determined from the reading of the coulometer. In the second method, that is coulometry at constant current, the solution of the substance, it is electrolyzed with constant current until the reaction is completed, and then we know that the quantity of electricity passed Q is given as I into T. So the time is measured with a stop clock, and the current can be the flow, it can be measured through a ammeter. Now coming to applications of coulometry. The coulometric methods, they have greater scope than gravimetry. So gravimetric methods, they have certain limitations, but coulometry, they find greater scope. So here in coulometry methods, they do not require weighing because they require weighing measurement of the current. So that is why once we know the current, then applying Faraday's law, we can find out the mass that has been deposited. Sorry. So in coulometry, at controlled potential, normally a mercury cathode is preferred since the optimum controlled potential for a given separation can be determined from a polarographic data with the DME, that is dropping mercury electrode. So in general, there is no advantage in employing a control potential more than 0.15 volt higher than the wave half wave potential E 2 by 3. In table 6.5, it shows the deposition of metals at controlled potential of the mercury electrode. So by means of controlled cathode potential technique, it is possible to determine simultaneously copper and bismuth, cadmium and zinc, and we can find out simultaneous co-detection of different metals. Now, general procedure for performing coulometric determinations at controlled potential of the mercury electrode. So, first, 40 to 60 ml of the supporting electrolyte is taken in a cell, and nitrogen is passed through the solution to remove the dissolved oxygen. The mercury cathode, it is dipped, it is involved through the into the solution, it is dipped into the solution, then stirring is made, the potential state is adjusted To maintain the required control potential and solution potential, the preliminary step of electrolysis will remove the impurities. So, and we will continue it for 10 minutes. Then 10 to 40 ml of the sample solution will be taken in the cell, and the electrolysis will be allowed to proceed till the current decreases to the small value. So then we have this formula using the Faraday's law. The mass of the metal that is deposited on the electrode, it can be calculated here. Here we have a term that is IB. Q represents the total electricity that has been consumed, and IB represents the background current that has been in amperes, and it has to be subtracted from Q. Now, separation of nickel and cobalt by controlled potential coulometer. So, the reagents required are standard nickel and cobalt ion solution, and they were prepared by dissolving a pure ammonium nickel sulfate and ammonium cobalt separately in water. So, pyridine is also used. The supporting electrolytes are 1 molar pyridine and zero point 0.5 molar chloride ion, and the pH is adjusted to 7 when silver anode is used. So 1 molar pyridine, and we have taken zero point 0.3 molar chloride ion and zero point 0.2 molar hydrogenium sulfate was added, and the pH was adjusted to 2 when platinum electrode is used. Then the procedure is, we take 90 ml of the supporting electrolyte in the cell. The air is dissolved with pure nitrogen at at minus 1.2 volt versus SCE. Then it generally takes 30 to 60 minutes. Then the coulometer is attached to it, and the potentiostat is adjusted to maintain the potential of the cathode at minus zero point 0.5 versus SCE for nickel, and minus 1.2 volt versus SCE for cobalt. So then we pipette 20 ml of the solution that containing nickel and cobalt. We'll continue the electrolysis under automatic control, minimum for 2 to 3 hours for each metal. Then we will record the quantity of current that has been consumed from the coulometer readings, and using this formula we can calculate the mass of the each metal that has been deposited at the electrode. Then coming to multi-step controlled potential electrolysis. So here detection of several metal ions is also possible using a mercury pool cathode. A sample solution containing several ions such as Cu2 plus, bismuth 3 plus, lead 2 plus and zinc 2 plus, they can be determined. So by keeping the self potential fixed at one value, copper 2 plus can be reduced to copper 0. Then keeping the another potential fixed, we can reduce bismuth 3 plus to bismuth 0, and similarly the other reductions can be made, and particularly this is a example for analysis of brass or bronze samples. Then coming to microanalysis. Controlled potential coulometry, it is more popular than electrogravimetry because it avoids the final step of weighing of the product. The tedious steps of drying and weighing are also avoided. This is very useful when the final product is not a solid. The technique is specially useful for the determination of small quantity of the analyte, and it measures almost with an accuracy of plus minus 0.5%. Then this method, the coulometry, is also used for analysis of radioactive materials. The coulometric methods, they are widely used in the determination of uranium and plutonium, and they find extensive use in the nuclear energy field. The reduction of UO22 plus to U4 plus, it can be carried out in H2SO4 medium with a mercury pool cathode at zero point 0.6 volt versus SC. The sample containing 7 to 75 mg of uranium may be analyzed with an accuracy of plus minus 0.1%. Then continuous monitoring of gas streams. So determination of trace level concentration of oxygen in a gas stream can be done by controlled potential analysis. So the cell reactions, which consists of a silver cathode and a cadmium anode. So at the cathode we see 4OH minus, and at the anode CdOH hydroxide is cadmium hydroxide is evolved, is comes out. The porous silver cathode, it serves to break up the incoming gas into bubbles. The hydroxyl ions that are formed here, they during reduction with the cadmium anode, they form cadmium hydroxide. So here a special feature of this setup is that a galvanic cell is formed, and hence no external power supply here is needed. This is one special feature. There is no need of a potentiostat to control the potential of the working electrode. The current produced is passed through a standard resistor and the potential drop is recorded. The oxygen concentration is proportional to this potential, and the digital display also indicates the oxygen concentration. So then, coming to electrolytic determination of organic compounds. Controlled potential colorimetry offers a new step for the electrolytic determination of trichloroacetic acid and picric acid, which are quantitatively reduced as a mercury cathode. The coulometric methods permits the analysis at an accuracy of 0.1%. Then electrolytic synthesis of new organic compounds. Synthesis of new species and novel chemical compounds are also possible. No chemical reagents are required because since electrons are involved here, they are sufficient for carrying out the chemical reactions. Plus, one of the advantages is that no contamination of the products can occur here. Then the last application is determination of the n values of the reaction. Controlled potential coulometry can be used to determine the n values, that is the number of electrons that are involved in the reaction. They are called as the n values. So the determination of these n value, they are useful to understand the kinetics and mechanisms of the overall reactions. Like for example, when picric acid is reduced at the mercury electrode, here the n value has been found to be 18. So thus from the value of this n, we can identify that the reaction product to be triaminophenol. Thus, this is how coulometry methods have been useful for the determination of the n values of the reaction. Now coming to application of coulometric titration. So here in application of coulometric titration, here the first we will talk about is the neutralization titration. So it involves the titration of a strong acid or weak acids. So here we can see at the cathode hydrogen is generated. So this is for the titration of a strong acid or strong base. So one of the main advantages of coulometric titration of acid is that the presence of CO2 in the test solution can be removed by passing nitrogen through the cell. Then the use of coulometry in precipitation and complex formation titration. So a large number of coulometric titrations, they have been developed with the anode generation of silver minus. So for such purposes, chloride, bromide and iodide, they are best determined with mercury generated at 100% from mercury coated gold or mercury anode. Then identification of chloride. The standard potentials of fundamental couples involving uncomplexed Hg1 and Hg2 has been shown here. So the complexometric titrations involving ethylene diamine tetraacetate generated at the mercury cathode, they have been developed, and mercury electrode can be used to identified upon forming metal complexes. Now coming to oxidation reduction titrations or redox titrations. The oxidizing agents such as iodine, bromine, chlorine, they can be used and they can be generated by making use of the coulometric methods. Here in table 6.7, it shows summary of some of the applications of coulometric titrations that involve precipitation, neutralization and complex forming reaction. In table 6.8, we see the application of coulometric titration in redox reactions. Now the advantages of coulometric titrations. Here the standardization, preparation or storage of some solutions, they are not necessary. It is easy to handle small quantities of reagent. A single constant current source, it can be used. Coulometric titrations, they can be readily adapted A number of automatic coulometric titrators, they are available in the market. In carbon dioxide monitors, where the gas stream can be absorbed in monoethanolamine, it is titrated with coulometrically generated base. Also in water titrators, Carl Fisher agent has been used to determine the various trace levels of moisture or water present. So with this, the different applications of conductometry, coulometry and electrogravimetry has been discussed. So with this unit, with this part, we finish this unit, and we'll start with a new unit in the next class.
मैडम, हेलो
हाँ.
मैडम,
हम्म.
हेलो मैडम, जो असाइनमेंट बारे में अभी जान सकते हैं क्या?
वो तो मुझे पता नहीं है. यू कैन टॉक टू योर study center or your coordinator. They will give you that.
ओके,
Okay.
ओके मैम, थैंक यू, थैंक यू।